So the magic, this is, my trouble with this lecture is that I just love every slide and I could talk for a whole hour about each one. The key that we're going to use to solve the problem of how to build good combinational devices is all built around this particular device. It's called a MOSFET. M-O-S-F-E-T. That's an acronym. It stands for Metal Oxide Semiconductor Field Effect Transistor. And we'll see each of those words will show up in the next slide or two, and you'll get a sense of why we call it a MOSFET. On this slide, there's a couple things that I want you to notice. One is that the MOSFET is a 4-terminal device. It has 4 different connections that you need to make electrically in order for this physical device to work. And so we have a gate terminal, which that's actually it's called the gate because it's the thing that will control whether current is conducted between the source and the drain. The device is physically symmetrical. In other words, the source and the drain, there's no physical distinction between them. And so we adopt the convention that we simply label which one of the sides the source and one of the sides the drain, depending on which side has the higher potential. So we always label the side with the higher potential the drain. So that's just a sort of a labeling convention. And finally, there's a 4th terminal called the bulk, which I'll say more about. The device has 2 critical dimensions. There's the width and the length. So the length goes between the source and the drain, and the width goes across the source and drain. And the way it works is that depending on what voltage I put on the gate, current is allowed to flow between the drain and the source. So think of this as a big voltage-controlled switch where current can flow from the drain to the source. And I always say it that way because the drain has the higher potential, so the current flows from the greater potential to the lesser potential. And so the current flows across the length. It goes, so if this is width and this is length, current, I'm the source and you guys are the drain, the current will be going whoosh this way, okay, across the width of the device. For the width of the device all the way across the length. So the electrons are flowing from you towards me. You're the drain, I'm the source, and the gate is covering this table here. So how do I make more current flow? How do I adjust the dimensions of this table to get more current to flow? Well, as the current flows across the table from you to me, right, it basically, the electrons are flowing. There's a certain resistance that it meets because of the conductivity of the material that's forming the conduction channel between the drain and the source. And if I want to get more current, I want less resistance. And the way I can get less resistance, one is I can make the table narrower so the electrons have to flow less far across this sort of not too good a conductor. Okay, or I can make the table a lot wider and get a lot more paths in parallel. Right, so the thing that I want you to take away from this, and this is sort of the key to the sort of simple design of these devices that we're going to be doing, is that the amount of current this device will, this voltage control switch will allow is proportional to W over L. And there's never any reason to have more L than necessary. So what you do is you call up the manufacturer, you say, hello, TSMC, yeah, this is Chris at MIT. What is the smallest I can make L? And then I will adjust W to get the amount of current that I want. And depending on when I call, that number gets smaller every couple of years. Right? So when I first started out, that number was several microns. Okay, the minimum dimension. Anybody know what the sort of current smallest dimension of a modern chip that you buy from Intel is? So we went from several microns, several micrometers. Micron is just a short for micrometer, 10 to the minus 6 meters. What is it now? I heard nanometers. It's not quite 1 nanometer, but is there a number? Tens of nanometers. So we're sort of in the range where the most modern chips you buy from Intel are in the 20 some odd nanometer process, and next year it'll be like 18 nanometers, right? And that number has been dropping by a factor of 2 about every 18 months for the last several decades. There's a lot of people who sweat blood off in the magic labs of People who do device physics, figuring out how to make new devices every year, that number keeps falling. And that's why electronics has really, the price has dropped and the performance has increased so dramatically over the decades, is that this fundamental parameter, this L, has been shrinking by that factor of 2 every 18 months. That's called Moore's law. Okay, so let's think a little bit about how this magic device works. So now what I've done is I've taken a cross section, okay, and you can see the source and the drain on either side. This big thing at the bottom, this sort of pinkish area, is called the bulk. So we start off with a big silicon wafer, and we fill it with impurities so that it actually is what we call a p-type semiconductor, which means that it has a majority of carriers that are holes. In other words, you can actually get currents to flow in this device. The N-type devices are very much the same. It's a different sort of impurities that basically allow where the majority carrier is electrons. So p-type silicon has a majority carrier of holes. N-type has a majority carrier of electrons, and we basically just use different sort of manufacturing techniques to basically embed these diffusions into the silicon wafer, and then we build a bunch of structures on top. A little layer of insulating oxide and this gate node. So initially what happens is when we put this together, see what happened there? See how some of the pink went away? If you put these P and N-type devices together, initially what happens is that the mobile carriers move around. And they actually move out of it right at the junction between the P and the N, the P-N junction. What happens is the mobile carriers, what's called deplete, the depletion zone, they actually move out of there. So if you were positive, if you were a hole, you'd wander across and mate up with an N. And if you were an extra electron in here, you'd move away from the N-type devices and come find a hole to become your mate for life. And what happens is you get this depletion region, which it forms a natural insulating barrier between the N and the P. So this is a so-called PN diode. Now what's going to happen is I'm going to slowly charge up the gate. I'm going to start at 0 volts and go to 1/10 of a volt and 2/10 of a volt and 3/10 of a volt. And at some point, I'm going to get a strong enough electric field across the gate that I'm actually going to change the type of the material of the bulk region here, which had been all insulating, to N-type. I'm going to suck up enough electrons that there's now enough mobile carriers right at the surface here, right below, right underneath the other plate of the capacitor, that I'm actually going to produce a little N-type region right in the gate area because of this increased electric field, and that's going to now short together the source and the drain. So what happened is initially those two guys, the source and the drain, were isolated. Those two N diffusions were isolated. But as I increased the electric field over the table, I started getting a lot of electrons underneath, okay, on the other side of that oxide of the gate terminal. And now this guy turned to an N-type, and now I'm shorting together the drain, which is you, and the source, which is me. So I now have a conducting region. So this ability to turn it on and off this conducting region based on a field, that's why it's called a field effect transistor. Now, it's all sort of complicated. If you take 6012, you can learn all about work functions and Fermi levels and how solid-state physics works. But for us, just think of it as a voltage-controlled switch. For this type of device, if I put a big enough charge, positive charge on this gate, I will make a conducting region between the source and the drain. Okay. Now, it turns out that FETs come in two flavors. Okay. The thing I've been talking about is what we call an N-FET, or an N-channel device. That's because the inversion, I put positive voltage on the terminal and on the gate terminal, and I attract electrons, and I connect the two N regions. So as the gate voltage goes up, what I'm going to do is attract electrons, make the inversion, and the switch goes on. So that's an N-type device. High voltage on the gate makes the switch conduct. There's a symmetrical device called a P-type device, in which the channel is actually is made up of holes. Okay, I'm going to make the connect two P regions by another inversion layer, and so the P FET and the N FET are complements of each other. And now we get to the complementary metal oxide semiconductor, CMOS, which is what every device you own is made of. Okay, and I'm going to draw my little Valentine to CMOS here in a few minutes, and we'll see why we love CMOS. But for now, think of CMOS as made up of two complementary devices. As complement with an E, meaning the opposite of each other. And so we have N-type devices that basically turn on when the gate voltage is high, and P-type devices, which are voltage control switches, that turn on when the gate voltage is low. Everybody sort of, and you can take 5 courses here and go all the way through your graduate work to learn about all the details of why these devices work they do. This is a very, very simplified sort of explanation of how these devices work.